Okay, hey guys, this week we've been looking at gravitation and we've also been looking at fields, which is a really new concept, so I thought it'd be a good idea really to go through this in super slow-mo, because I think it's something really conceptually difficult, and it's definitely worth just sitting back, watching this video and trying to get a good idea of what's going on. Okay, so let's start from the top. Gravitation, as we know, is some force that sticks us to the ground. It pins us to the earth. And we've known about gravitation for a long, long time, but it took until Newton to come along to actually quantify what was going on. So we talked a little bit about Newton's universal law of gravitation. And all he said was that all massive bodies feel a force due to gravitation. They always come in pairs. And he said that everybody feels an attractive force to every other body in the universe. And that force is proportional to the product of their masses, so big M, little m here, and inversely proportional to the square of their separation. So if these two masses are some radius apart, and we measure this radius from their centre of mass, so right in the middle for everything we do, the force is going to be inversely proportional to that. So he noticed, actually, if you move two masses far away from each other, their gravitational attraction will decrease. Gravity will have a lesser effect. So if you double the radius, you will quarter the gravitational force. And he also noticed that it's dependent on the products of the masses here. So if you increase one or other of the masses, then the force itself will increase. So he used all this, he shoved it together to get his gravitational force equation, which is F is equal to minus big G mm over r squared. Gangster. So that is our gravitational force equation, and the fact that it's negative just tells us that this is always attractive. We haven't yet discovered any repulsive gravitational force, but we'll see. Maybe antimatter will, but anyway, so this was the force, and that was the first thing we talked about. And so from this equation, you can see that really the only sort of geometric dependence, if you like, on the force is r. It's the radius, the radial distance away of body B, if you like, from body A. So this could be a planet or a satellite. This could be a sun or a planet, something like that. And it only depends on r. So what that means is I can move my mass anywhere I like, and the only thing that matters is this radial distance. So if I move the mass B over here, it'll still feel a force. It's now closer, so it'll be a larger force. And it really doesn't matter where I put it. So we talked about if I can put these masses anywhere, and at each point they're going to feel some force. Really what we wanted to do was, instead of sort of guesswork, instead of having a guess at what this force vector is going to be, because obviously we're bothered about the direction of the force, it does always point towards the centre of mass, but you can see that this arrow here and this force arrow here have very different vectors and magnitudes. We wanted to kind of reduce that down into something called a field. Now, all the field was, so I'll get rid of all this, all the field was, or all the field is, sorry, is it's a sort of map. And a field tells us what some particular physical value is at every point in that map. So I could have my big mass here, and I can define a gravitational force field. And all this will be is the force acting on a mass, a test mass of mass little m, when I place it at every single point in this map. So if you like, I could use the squares on this grid and I could put a test mass at every single point. It would be really laborious and it would take a long time, and at every point I could draw the vectors that are acting on my test mass. And obviously I could do that for every point. It would be really boring, and in fact it wouldn't be very much help. It would be really confusing. So you can see that at every point along here it's changing direction. If I move them closer as well, they'll not only change direction, but they'll change magnitude. So I'll have something like this. And this then, I could do this for about, take me about half an hour. I could build up a field, a vector field, which defines at every point the force vector acting on a little mass m due to a big mass, big M. But we're going to have a bad time with that, okay? And I'm bored. You know I've got a short attention span. So instead what I'm going to do is I'm going to simplify this somewhat. And instead of drawing a billion lines, I'm just going to draw 8. And from these 8 lines, we will be able to infer everything we need, or everything we need to know about this force. So here are my 8 lines. Within this picture, I can get tons and tons of information. So first off, I know that this field, the vectors, always point towards the centre of mass. These lines are radial lines. So that's the first thing I can tell from here. If I know there's gaps between these, if I put a mass somewhere in between, all I have to do is sort of look at the neighbouring lines and infer from those what it's going to be. So I know there'll be a field line there. If I put another mass over here, say, I know by inferring from these lines that there'll be a field line like that there. Okay. All we're doing is we're simplifying the problem so it makes more sense to us, or it's easier to make sense of. So that's the first thing we can tell from here. So from our vector field, so I'll just write this is a vector field. From it, we can tell, number 2, that gravitation is always acting radially, so field lines are radial. And the third thing we can tell from this, number 3, is the strength of gravity. Now we said over here that the force is inversely proportional to the square of the distance away. So the distance between our big mass m and our test mass. So we can look at on our field map here what changes with distance, and we can see that the closer you are, if I draw a sort of loop here, and I draw the same loop, same size, some radius away, I can see that more lines go through this loop than go through this loop. And actually, if we go back to this idea earlier where if I'd have drawn loads and loads and loads of field lines, we could extend this. So you can definitely see the more I draw, even though we're not too bothered because we don't get that much more information, we can see that more field lines go through here than up here. So if you like, as a vector, those field lines would add together and give us an increased force on our test mass. So we can tell from this, the last thing, number 3, we can tell that the spacing between the lines, between the field lines, tells us about the strength of the field, or the magnitude of the field strength. Okay, so that in basic words is combining our my boy Newton's universal law of gravitation, which gives us this equation with this idea of a vector field or field map. Okay, so that was the first lesson we looked at last week. Now let's step it up a bit. This field comes from us looking at what these vectors, these force vectors, are going to be for my mass m here. But because we can see that this equation has a dependence, the force between these two bodies has a dependence on the mass of my test mass, if I change this, if I make this a bigger mass, actually I'm going to change the field. So these lines will become stronger. I've increased little m, which increases f. So all of these lines are going to become bigger. So basically what I'm saying is, this field, as we've defined it, the force field, has a dependence on me. So this could be, if you like, this could be me floating through in space, or you, but it has a dependence on you floating in space. And that's really bad. Okay, imagine you're hiking and you want to know where you are. Say you're scaling a mountain. If your map changed as you moved through it, that would be really, really bad. Okay, you wouldn't be able to make any sense of it. And this is kind of like what's happening here. This field has a dependence on my presence in it and the properties which I have, namely my mass. So that's really bad. So instead of talking about the field, what we'll do is we'll redefine the field. So instead of having this situation with small m and big M here, so these are really what should be the same field, but aren't because of this this dependence on the test mass. What we can do instead is define something called the gravitational field strength. Okay, and all the gravitational field strength is, if I get rid of this, we call this little g, and we define it now as a vector field where at every point on the map or within that field we define the force of gravity per unit mass. So looking back at my universal law equation, all I'm doing is getting rid of this. I'm dividing through by m, little m. So now we get minus big G m over r squared, and this now is our gravitational field strength. So now, even though I've got two different masses, okay, a small mass and a big mass, because this field has no dependence on that mass, the field lines are going to look identical in both cases, so exactly the same field, and that's much better. Like I said, if you're hiking, you do not want your map changing as you move through it. Or another way of talking about it is you don't want, say you and a friend go hiking, if you have different physical properties, okay, if your friend is much more massive than you, you don't want their map looking different than yours just because your masses are different. So what we're going to do now is we're going to bin the gravitational force field that we had up here, and we're replacing it with the gravitational field strength, which again is a vector field. It's exactly the same, but now it's completely in the background. It's just this thing that exists there and acts on you. Okay, you move because of it. And if you like, G being a force over mass, if you remember my boy Newton's second law, so that's N2, force over mass, or the units of force over mass, are the same as the units of an acceleration. So we can say now that this field, okay, this gravitational field strength field, all this shows us are lines of motion. So if I drop you in space here, I know that you will follow this field line because it moves through your centre of mass, and therefore you will accelerate along that line towards this gravitating body. If you like, now what we can say is the gravitational force So this is our vector field. We can now say that the gravitational force F, which is minus gmm over r squared, we can say that this thing is actually just an effect of the field. So it's an effect of the vector field itself. So now the field strength is the field we're bothered about. The force that you feel is just an effect that that field has on you because you have mass. If you have a bigger mass, you'll feel a bigger force, but it's because of exactly the same identical field that everyone else will measure. All of our maps are the same. Okay, so now to go back to the map analogy, we all have the same mass, but if you and a friend go hiking up a hill, if your friend is more massive than you, they will find it more difficult because there is a bigger force acting on them, even though your maps look the same. Okay, right, this has become quite a long video. I'm going to cut this off here. Hopefully that's explained a little bit more about the difference, the subtle difference between the gravitational force and the gravitational field strength for you. And in the next video what I'll do is I'll extend this to potential and potential energy and then link it back to this field, because as we saw this week, these two fields are very much interwoven. They are pretty much, well, they are, if you like, two interpretations of the same thing. Oh, before I go, all of this I've talked about, these are radial fields. Just before I go, if we zoom in really close to the surface of this planet, so if I zoom in to a planet of mass m, now we get what we call the uniform field situation. And now the uniform field, all that is our field lines are equally spaced and parallel. And all this says is, if we go back to our rules for the field up here, okay, it's a vector field, they're always radial, okay, in this case they're going to be parallel down here. But rule number 3, the spacing between the field lines tells us about the strength of the field. So all this is saying is close to a planet or near a surface, it doesn't really matter if I'm here or here or here, pretty much I'm feeling the same gravitational field strength because G here is uniform, i.e. the spacing between these field lines does not change with distance away from the planet as long as you're close to it. And that makes a lot of sense because you don't feel gravity, the acceleration due to gravity, change significantly when you walk up a flight of stairs or something like that. I'd be worried if you did. So just to distinguish this from the radial case, we do also have a uniform field case, but this is only when we are close, very close. So when I say close, your radius is your radius pretty much is equal to the radius of the planet itself. So if this is the planet, this would be its radius r. Your radius, little r, is very similar to that. And this applies in this case, but you can distinguish it from the radial case. Okay, thank you very much for watching. As I said, next time we're going to look at potential. So, see you then. Goodbye.